Okay, today we're going to look at or continue with kinetics of a particle, work and energy. We'll look at 14.1 and 14.2 right now, then we'll look at 14.3 a little later. Basic idea, we're going to look at this idea of work of a force. Thinking about this concept of work, essentially it is applying a force, and applying that force, well, particle moves over some displacement, from one point to another point. Okay. Then we're going to look at this idea of work and energy, the principle of work and energy. And the concept is essentially is that, you do work on an object, essentially you're going to give it some additional energy. So these are related concepts. Okay. What are we going to use this for? One of the things we're going to think about we can use this concepts for is, like, let's say a design of a roller coaster, right? And these are some of the things you may want to be concerned with. You're looking at, the height, the initial height of the cars. Well, how high do you pull it up when you release it? And essentially the radius of the curves, or in this case, it looks like a helical track, to ensure that it doesn't it goes all the way around, and it doesn't pull like net force of the people downward, or the car downward, and that it will have enough initial velocity or velocity to get around any of these curves. Okay. Another thing we're going to look at is this idea of or here's another application, I should say, crash barrels, right? And the idea is, of course, is to do work. Essentially, if a car were to hit the crash barrels, what you want to do is have it, do work on the car to essentially take its velocity from whatever velocity was initially when it hit the barrels to a final velocity of 0. Okay. And you're doing this over a certain distance, right? The distance of the barrels, as opposed to having, like, if they weren't there, you'd have an immediate deceleration, which is would not be good. Okay. So we basically the idea here is you want to cushion the crash. Okay. Okay. So first part here, or the other thing we're going to look at is this idea of work and energy, the relationship between the two. Okay. And the basic idea is that, if we first start with this, we start with this idea of force, right? Force, and thinking about it in a tangential direction. So you have a particle, and if you sum all the forces acting on this particle off in this direction, the tangential direction or direction of motion of that particle, you could represent that as our force, and then the particle, of course, is going to go through some displacement. Now, the only thing here we're going to do is we're going to change this, so the acceleration in the tangential direction, we're going to write it as v over dv ds. Essentially, what we had previously derived and we applied the chain rule to come up with this. Okay. So this is where we're going to look at this idea of the principle of work and energy, the relationship between the two. Okay. What we're going to find is that these equations will help us, right? Looking for force, velocity, and displacement. So these are like an alternative way to do some of these things. We used kinematics previously in chapter 12, and then we used kinetics to solve different problems too, with the forces and mass equal to the mass times acceleration. Okay. And we're also going to use this for the idea of power, which is just basically work or energy per unit time. Okay. Okay. So one of the things we're going to think about here is that work, how much work is being done, or how much work is an object doing or being done on an object, in this case a particle. And the basic idea is this, is that if you notice, the force essentially times this times the cosine of the angle. So let's say you have some force vector acting off in a certain direction. We have two vectors, an R1 and R2, to essentially represent the two positions. So you're starting off at S1, and then some time later you're at S2. Well, we can represent that as just force times the cosine of the angle, which is essentially force times the cosine of the angle, is the force that is, or the component of the force that's acting in the tangential direction. And then we multiply that times this little incremental distance that we moved, okay, or the displacement. So this gives us that little incremental, our incremental work that's being done by the force, right? We can also represent this, and you notice this is a scalar. It's like work done to go to work done uh, on an object, or the total work. You can just write it as total work. Going from 1 to 2 is essentially just the integral of our dot product, right? Which is what we had previously done. And these are the two vectors, right? These are our two vectors for that. Our vectors represent our position relative to something, relative to some, if we want to call this the origin or some point, okay? And then here is our second position, all right? If it's a function of position, if our force is a function of position, so it changes as a function of position, so this is f as a function of s, we can actually just write it this way. So we have same thing, here's our component of the angle. So this is the first way we had written this, right? And then if we integrate it, what we can do, this is our like du, right? Our delta u, or du. If we find the integral there, we can actually find, which essentially is the difference between the two, which is like essentially the work being done to go from 1 to 2. Okay. Now the more specific case in this, hey, if the force is constant and we're applying some force, constant force, to go from some position along a straight line, then we just have, it just becomes the constant force times the angle. So this is essentially the component. This represents essentially the component in this direction, right, along the direction of motion, and then the two positions, S1 minus S2. Okay. In terms of whether or not it's positive or negative, it's just like, well, if the force is in the movement in the same direction, it's positive. If they're opposing, then it's negative. Okay. And the last part is that if the force is tangential to this, the work is going to be 0, right? So we can't really use that to determine the work if just in terms of that force, okay, which we'd find out anyways, right, just from this equation. Okay. Work done by gravitational force, and of course if you just plug in, you'll find, well, this is a constant, W is going to be a constant, and then this is like the difference between the two positions, the vertical positions, that just becomes delta y, so y2 minus y1. And in this case, you'll notice that the motion is opposite of the force acting down. So it starts off at a lower position, then it's going up to some other position, y2. And you're going to have a negative in this case. Okay. Okay. So in this case, if delta y is upward, then of course the work is negative, which is what we would expect. Okay. The next one is the spring. Now, spring, work done by the spring on the particle, or if the work done by the particle, will tell you that it's positive or negative, right? And of course, all we have to do here is just come up to, determine the integral for this. When you substitute in for F for the force, which is really just the spring constant times its displacement. And when you do that, and you integrate, this is the end result, right? It's just going to be half of it, half times K S2 squared minus half times K S1 squared. So that's going to be the work of the spring, okay? And then we just have a negative sign, of course. If it's, this is done on the particle. This is done by this exert. This is force on the particle. It depends upon, okay. So just to clarify, work of the spring moving from position S1 to S2 is going to be positive. If we think about if it's, we have some particle and we want to know the force exerted on the particle, then becomes opposite to that exerted on the spring, right? They're just going to be opposite of each other. The work done on the particle is going to be negative. Okay, So just the difference between the two. Matters of just the difference of perspective. Just some things to be aware of course. These are linear springs only, right? And that's really all we're going to do in this class. And make sure that the work is not just the spring force times the distance, right? It's going to be Ks, ISI, right? So you have that S squared term, okay? And just thinking about, the sign of it. It's positive the work is done on the object by the spring, okay? And the idea is that, the movement or in the direction of the spring or the motion of the spring, the work done by the spring is in the same direction of motion. Okay, so principle of work of energy, what we had previously talked about the force representing, we said the summation of forces in the tangential direction, and we substituted in for the acceleration in the tangential direction. Now we have a different form of this equation. So now we would do the integral of f dot ds, right? So, but now when you do a dot ds, this ds cancels out with the other ds, and you have initial velocity and a final velocity. So you have it in terms your variable of integration is now going to be velocity, okay? So when you do that, essentially this is like our relationship between the two. It's like, all right, here's the work being done, and here is the kinetic energy associated with it. So you do work on an object, essentially you're going to increase its kinetic energy, okay? So here's the initial kinetic energy, and here's the final kinetic energy, all right? And of course you can rewrite this. So you could say like T1 is our initial kinetic energy added to whatever work's done on the object, and then we have some final object or particle, and then we have final kinetic energy, right? So U1, summation of U from 1 to 2 is basically all the work done by all the forces acting on that particle, okay? And yeah, T1 and T2 are just the kinetic energies, okay? We will notice that it's the kinetic energies, the initial and final, of course, are always positive. Although you could reduce it, right? It could be if this is negative, of course, then it's going to be your final kinetic energy be less. All right. Okay. Just some things to note about that, right? Scalars, okay? Joules are the units used in energy and work. Is going to be the same. Joules are used in SI system, and of course 1 joule is just equal to 1 Newton meter. And the FPS system or USCS system, it's going to be in foot-pounds, okay? And the last part we just can't find, we can't use it to find forces normal to the path, okay? Only in the same direction. Okay, so we can also do this with a system of particles, which we'll cover later. There's one more concept we need to pay attention to here, and that's when we have friction, okay? Now, this is a very simple example of this. When there's friction in a system, in a problem that you have to be concerned with. If we think about, in this case, we have an object, or let's say a block, sliding on a surface, and it's a rough surface. And you have some initial velocity and final velocity, and these two velocities are the same, and we apply some force, okay, P, right? And P is essentially just a force using to make sure that, our velocity is maintained, okay? Now, if we use this concept, principle of work and energy, what we would have is that we would have a force acting in the same direction, essentially, work being done on it. And then we have this other component here, which is our frictional force, okay? And what happens here is essentially these two cancel out, because essentially what you're saying is your initial kinetic energy is equal to your final kinetic energy, okay? For this to be the case, of course, this force basically is going to equal the frictional force. And what happens to that energy? Well, that loss in energy, essentially that gets converted over to heat, right? All right, so... Okay.